Okay, I'm going to get started. Hi, everyone. My name is David Pacheco. I'm a software engineer at Joyent, and I'm going to be talking today about a system that we built at Joyent for automating Postgres failover for high availability. So the structure of this talk is going to be that I'm going to talk about the problem we were trying to solve, the system that we built in order to do that, and I'm going to talk a bunch about the operational experiences that we've had, both with that system, but also with just Postgres in general. So if it wasn't clear, this is primarily a talk about the system that we built, which is open source, and our experiences with that. It's not so much an instruction for you to how to do it, although you can certainly use the system to do it. But I'm not going to try to tell you how to do this. This is just what we did and how it worked for us. So the background for this, most of this work was done in 2012 and 2013, and we did a major rework in late 2014, almost exactly a year ago. So at the time that we started this work, I don't know of anything else that existed at the time to do it, which is why we did it. I know now there are a couple of other systems that do this as well. The other thing to keep in mind is that none of us who built this is primarily a database engineer or a database administrator, at least certainly not when this work was done. So it may turn out, and did basically turn out, that we did some silly things and things that people who are really familiar with this stuff will already know were silly. We learned a lot since then. And I think it's still interesting as an example of a bunch of generalist engineers just taking Postgres and running with it, and the experiences we ran into. So with that, I want to talk about, first of all, the problem we were trying to solve. We were building a system called the Manta storage service. Has anyone here heard of Manta or maybe used it in the room? Okay, actually a good number. This is an HTTP-based multi-tenant object store. So this is an HTTP service that's sitting on the internet. Anyone can use it. You authenticate with private keys, and then you do put, get, delete of giant byte streams. That's basically what it is. The thing that makes it different than some of the other stuff out there is that it has Unix-like compute as a built-in thing. But I'm not actually going to talk too much about that in the context of this talk unless we get to some more of the incident stuff later. Just to give you a sense of what we're actually trying to build, I would just want to demo that for just a second. So the idea was to make this feel like a Unix system, but it's actually a distributed system, again, potentially over the WAN. So we have a suite of tools that look like the Unix tools. So I'm going to, my account name is DAP. So actually, before I even do that, I've got environment variables here that refer to my account name, my SSH key fingerprint, and the API that I'm going to hit. And then I can use these tools like MLS. Oh, that's not good. Sorry. I just rebooted my Mac, and that was obviously a bad idea to do right before this. Sorry. Boy, was that a bad idea. All right. Now you can actually list a public directory. This is kind of like home directories on a Unix system. We've got my account. This is my public directory. And then I have stuff in there. So I have like a talks directory where I have a bunch of PDFs, things like that. I've got like a bin directory, and the idea, and you can do things like find. I'm going to find all the objects in that directory. I think you can see the metaphors we were trying to go with here. And then the idea was if you wanted to do something like, I'm just going to use WC as an example. I want to run WC on all these files. This could be grep. This could be any other thing. What you were actually doing is instead of having your laptop download all these objects and then run WC and then upload the results back or something like that, we actually just took your WC. We went and found the storage servers that are storing all of these objects. We ran WC there in an OS-based container, took the output of that, saved that back into the object store, all within the object store, so without moving data around. Obviously, this isn't that interesting when you're running it WC on a couple of objects here, but it becomes much more interesting if you're running grep or log analysis on thousands of log files or something like that. So that's kind of the basic system we were trying to build. And the key bits of the storage architecture here, obviously there's a front door, which is a node-based service that handles the API requests to put, get, and delete objects. There's a storage tier, which actually stores the physical objects. And we store each object as a physical file on a ZFS file system. We did that in order to be able to support compute, because if we did something like erasure encoding across a number of systems, it becomes much harder to just like hand that to standard in for a standard Unix tool or whatever other program that you have. But we're using ZFS, which is an important point here for the purpose of durability, data integrity. Both storage and infrastructure in general, but especially cloud services, they're trust businesses. Turns out if you lose people's data just once, they get really upset for a long time. So durability was really, really important for us. And ZFS has a whole bunch of features around that, including things like checksumming and storing the checksums in the parent block pointers as opposed to the data blocks to handle various other failure modes. I'm not going to get into all that stuff now, but I do want to emphasize the importance of durability for this system, even more than availability, which is what the talk is about. So we've got this front door, we've got the storage tier, and then we've got, in the middle, we've got this metadata tier. The metadata tier is the thing that takes a user's object name, in my case it was like dap public bin, some script that I had there, and maps that to a set of storage servers and the physical files on those storage servers where the contents of that data live. This is kind of the core of it, right? This is the important bit in the middle. This is where all the put, get, and delete operations actually happen. So again, for the metadata tier, durability, really important thing here. We decided we wanted to build a strongly consistent system. This was partly based on experience with other systems. People would use these between programs. You'd, for example, upload an object and then tell another program about that object, and it would go fetch it, and it would get a 404 because it was eventually consistent. And then you just like retry for 15 minutes and then decide that I guess that's too long and that's a problem. We didn't want to have to deal with things like that. We wanted the service to be able to tell you, no, the thing's here or it's not here. If it's not here or I don't know, that's also possible. That would be a 503. But we're going to be very clear about what the current state of the system is. Part of the reason for this, besides that use case, which is, I mean, it's important, but there are many other use cases where you could argue maybe that's not what you want. But we decided you could build an AP system on top of a CP system, but not the other way around. So actually, before I even get there, sorry, I kind of jumped over this. Do people know what I'm talking about? This is the CAP theorem. How many people have heard of the CAP theorem? Okay, this is most people. That's good. CAP says that for distributed systems, in the face of a partition, you must choose between either consistency or availability. At least that's the way I like to think about it. We chose strong consistency because you can build a highly available but eventually consistent, like not consistent cache on top of a strongly consistent system. But you can't build a strongly consistent system on top of that. And since we're building, on top of AP. Since we're building a piece of infrastructure, we wanted this to be strongly consistent. The workload here is also important. It's heavy read-write of small records. And the other bit about this is because it's a cloud service, it's a 24/7, 365 duty cycle. This is going to become pretty important later. So those were our initial design constraints for the metadata tier. As a modern cloud system, you want this to be fault tolerant and horizontally scalable. Obviously, those are buzzwords, but more specifically in the context of a database, we're talking about replication for fault tolerance and sharding for horizontal scalability. Our going in position was basically like, let's use Postgres for this. We did think about using a couple of other things. We'd had some bad experiences with a couple of other data storage engines. Our position with Postgres was we're not totally sure that this is the right thing, but if it's not, we want to know why. We want to know that we didn't use it for a good reason. And so we started down this path and basically never looked back. We knew that it was going to scale well vertically. It's got a bunch of tools that help you operate it. The internal views for showing just what's going on inside the database have been huge for us. They allowed us to root cause an outage that I'm going to talk about later, which is really important for us. And the built-in replication story, actually some of the same things talked about in some of the previous talks, so people understand that. In terms of the fault tolerance architecture for the system that we built, we did something which I think is pretty much what a lot of people start out with doing, which is you've got you've got 2 or 3 peers. We ended up going with 3. This is actually what it looks like. How many people have seen a diagram that looks a lot like this before? Okay, so what we've got is we've got a primary peer, a sync peer, and then some number of async peers. And they're called that because of the kind of replication that we're using. The primary peer is responsible for all the read-write traffic of Manta, or of that particular shard of Manta at any given time. We're using synchronous replication to a synchronous peer. That's to make sure that in the event of a failover, we don't lose any data. We don't want to lose even a few seconds worth of data when that happens. And then we have a bunch of asyncs that are sitting behind that in kind of a daisy chain. And those exist basically to be able to handle multiple failures without having to have rebuilt the primary. So the async is not used as part of a regular, or the later asyncs are not used as part of subsequent failovers. But they will be used later. So just to be really specific about what happens here when individual components fail. We've got the initial state of the world. We have these 3 peers, a primary A, a sync B, and an async C. At some point, we decide, let's say the sync fails, so B fails. At that point, A, the primary, decides that B has failed, hard problem, which I'll talk about later, and decides to promote C. C becomes the new synchronous peer. That usually will not take very much time for the replication to catch up to be synchronous because it's already asynchronous, and the lag we generally see is on the order of a few seconds. And sometime later, B will come back, and B will be assigned as a new async. So in this case, B and C just swap positions. Does this make sense? I do feel like this is a pretty common architecture people are familiar with. There was one constraint that we found a little bit surprising at first. I'm not sure, I haven't seen it spelled out explicitly in the documentation, but it definitely is true. If you have a primary which is replicating to a synchronous peer, and you do a failover, you can't replicate back after that. If the primary comes back, the primary potentially has records in its wall or something that is, it is a head in some sense that is not able to be reversed without doing some specific step. I just learned about PG rewind today, that's great. We may use that as a way to sort of speed this up, but you have to do something here. So what happens when the primary fails is a little bit more complicated. When the primary fails, we start in the same initial states here, A, B, C, primary sync, async. At some point, A fails, B decides that A has failed, and B decides to take over and promote C. This makes sense, right? At the point where we started, the primary and sync were always in sync, so either one of them can take over when the other fails. But the other thing we have to do is we have to mark A deposed. Deposed is a state that we created that says, this thing was a primary, but is now in a state where it has a bunch of data on it, but can't be replicated to. It effectively needs to be rebuilt from scratch. We can't allow it to just rejoin the cluster as an async. Sometime later, we'll do a rebuild. Today, that involves basically a complete rebuild of the database. We're using ZFS, so we're doing a ZFS send of a snapshot from, I believe it's the async, it might be the sync. So it's relatively efficient, but it still ends up taking like 20 minutes, during which you couldn't sustain another failure at that point and remain up. Durability, though, is still not an issue. OK, so this is kind of the basic fault tolerance business. The other problem with this is that at some point, the client needs to know who's actually primary. We built a special client we decided we wanted some decoupling between the application and the database anyway, and so we built a separate service called Moray, which I'll also talk about briefly. Moray, as a side function of what it does, keeps track of which peer is primary at any given point, and so it takes care of that. So the clients always just talk to Moray, and Moray knows which peer is primary. So this is what the cluster actually looks like. I'm sort of going deeper and deeper in terms of the implementation. We're using Zookeeper to manage the consensus, but Zookeeper isn't just a magical thing where you just all of a sudden agree on stuff. We actually initially tried to use it that way. We tried to say, we'll use join order in Zookeeper to represent the order primary sync async, but that doesn't work in the event of cold start. If all the things go down, you don't know what was what. We kind of iterated on that a bunch before deciding that we needed a more structured approach to this. So the way this is basically working is we've got the 3 Postgres databases, but alongside them we have a component which we call Manatee. And Manatee is basically a babysitter. It sits there. Manatee is connected to Zookeeper, and all of the Manatee peers are connected to Zookeeper. And there's a cluster state that is stored in Zookeeper, which represents who's primary right now, who's sync, who are async, in what order, how many are deposed, what generation number are we on, and a couple of other pieces of metadata that describe the current cluster state. So we've got the Zookeeper cluster, we've got the state that's stored in there, we've got the Manatee peers, which are responsible for maintaining that state. When they want to issue a failover, when they want to execute a failover operation, they do that by writing a new cluster state into Zookeeper. Zookeeper has watch functionality, so it will broadcast that fact to a bunch of other people who are interested, including Moray. Moray immediately sees, oh, the primary has changed, so I need to start contacting this thing. And Moray is itself a node-based key value store. I'll let that sink in for a second. But we do have a custom node-based key value store sitting on top of that. And that is actually just talking to the Postgres databases directly. So Manatee really is kind of a babysitter. It's sitting there. It's responsible for starting Postgres and configuring it, but it's not in the data path, per se. Does this all make sense so far? OK. This is what I just talked about. I want to just show the tooling that we have to represent this. So I'm logged in over here to a test machine that I have. I'll actually show the various Manta shards here. So what I just did here was I'm using this Manta level administrative command to show the Postgres instances that are part of this Manta deployment. We've got 2 shards here. Each of the shards has 3 peers, like I talked about. And I'll just log into one of those. We've got this Manatee ADM show command. What Manatee ADM show does is it gives you an overview of the current topology of the cluster. Who's primary right now? who's sync, who's async, and what their replication status is. One thing that we found, particularly with the previous version of this, which I keep sort of alluding to, had a lot of operational issues. And one of the things that would happen is it would actually take a long time for an operator just to figure out which one is primary, which one is sync, which one is async, and whether the kind of replication that was engaged at that time was correct. We would find cases where the primary was replicating to the sync asynchronously, and that was obviously bad. So it was important for us to actually have tools that make this extremely clear. We added a PG status command, which shows just that Postgres bit, which you can actually see the data flowing through the cluster because we're showing the sent, flush, and replay locations for both the primary and the sync's replication to the next peer. And we can see what the lag is. What else do we have here? If you're interested in the gory details, the zookeeper state looks like this. Ooh. That's weird. I don't know why that's getting weirdly corrupted. So it's just a JSON object. We've got a generation number. That's used to keep track of how many times we've had a failover. We've got the identities of the primary sync. The async is an array, and then we have the deposed peer. And then we also have this thing called the initial wall position. This is the wall position of the primary at the time that this generation began. This is important basically for the specific possible race condition where you have a sync take over from a failed primary. Now the async is promoted to the new sync, but there's some period during which replication still has to catch up because that third peer was initially a little bit behind the second peer. In that time, if the sync fails again, so now you had 2 failures in this short period, the async can't actually take over. That's not a valid transition because that would cause you to lose data. The async has not fully caught up to the sync, so it's not able to, at this point, both of the nodes that had all the up-to-date data are down. And again, durability was more important for us than availability from the perspective of this project. So we didn't want to do that. What the init wall metadata does, the primary, when it issues when it creates this new generation, in which I'm the new primary, it records its current wall position. And when the sync reaches that position, then the sync knows that it is eligible to take over if the primary fails. And if it doesn't happen, then it needs to wait for the primary to come back. We also use the zookeeper functionality to keep track of which peers are actually running right now. Zookeeper has this notion of sessions which survive TCP connection failure. So it's this notion that I have been recently connected. I am either currently connected or recently connected to Zookeeper. We use the presence of peers in the Zookeeper, like current Zookeeper sessions, to indicate peer liveness. This has been a reasonable proxy for us at this point. What that means is that it's pretty hard to wind up in a situation where both the primary and the sync think that the other has failed, because there's like it's either a 30 or a 60-second timeout on the Zookeeper session itself. So if the primary, for example, the OS panics or the system loses power, it'll be 30 or 60 seconds before we even do anything about it. And so it's pretty unlikely for both things to think that the other is gone if they themselves are both not connected to Zookeeper. That said, obviously it's a race we want to consider. The way we deal with that is that if you try to write to the cluster state, you do a test and set type of write. So you know that you're not racing with someone else that's trying to also write to it. Any other tools in here I wanted to show? I think that's pretty much, that's the useful stuff. So I talked about the cluster state. This is the state machine that represents how we ensure that this works. This is obviously, I don't think this is actually that readable, but also most of it is not going to be that relevant. It's a lot simpler than it looks. The key observation for us is that at any given time, the cluster is only in a pretty finite set of states. And there's a very small number of transitions that are valid from any given state. In particular, if you have primary sync, any number of asyncs, so let's say at least one async, there are only 2 possible transitions out of that state. One is that the primary decides that the sync has failed and promotes the next async, and just like swaps those 2. Or the sync decides that the primary has failed. Anything else is not valid. It's not valid for an async to decide it's going to take over. It's not valid for both the primary and sync to change in the same like transaction. So bounding it, making the cluster state very explicit and sort of formal, and bounding the number of possible transitions that can happen allowed us to be much more confident that this system was going to work and not lose any data. And also not converge to a state in which it was not online, which was a problem that we'd had in previous versions of it. So the way this basically works is that if a Manatee peer comes up, it looks for the cluster state. If the cluster state is there, it'll already say which role it is. It might be primary, it might be sync, it might be async, and it just starts up Postgres in the appropriate mode. In particular, if it's primary, it starts it up in the normal mode with synchronous standby names reflecting the IP addresses of the sync peer. Pretty straightforward. If you come up and you discover that you're the sync or the async or basically any other peer, you figure out who you're supposed to be replicating from, and that's in the cluster state, and you just set, we create a recovery.conf and we start Postgres in a mode that's replicating from that peer. So that part's pretty straightforward. At that point, it's like, okay, well, if you're the primary and you see that the sync's zookeeper ephemeral node has gone away, which means that the sync's zookeeper session has expired, then you decide that the sync has probably failed, and you write a new cluster state that consists of you as the primary, new generation, your current wall position as the initial wall position for that generation, and the next async is now the new sync. The next thing is all of the peers have a watch on the cluster state, so they can all see when it changes. So as soon as the primary writes that new state, all the other peers see that, and they basically go through the whole path again. They basically say, oh, I see, I've now been assigned as an async replicating from this, or I now see I'm assigned as a sync replicating from this, and they just configure Postgres appropriately. So it's actually much simpler than it seems. Much of the stuff on the top right is actually about the initial setup process, which just requires that there be at least two peers present, and we arbitrarily but deterministically pick one of the peers that will become the initial primary. I talked a little bit about our custom client called Moray. Moray does connection pooling. That was one of the main reasons that we initially built that. The idea was the application, database connections are expensive resources, and it was a lot easier for us to think about managing them through, it's not quite a central service, it is a distributed service, but through a single component than to have all the different things that are using it try to manage that themselves. We also wanted to decouple the application itself from the database. We didn't want SQL queries sitting in the middle of the Manta code. And as a sort of side effect of that, it's a natural place to put the bit about keeping track of which thing is primary right now. Obviously, you can do things like play games with the IP addresses and VRRP and things like that. I personally find that stuff a little bit harder to debug and operate and keep track of that stuff. But obviously, those are other approaches that people use. So for us, Moray Manatee is sort of a combined stack. You basically would be using Moray if you were using Manatee. But I know, actually, there are people in the community that are using Manatee without Moray, using other mechanisms to keep track of which peer is primary. If people are interested in Moray, I'm happy to go into it more, but it's a little bit ancillary at this point, so ask me a question about it, I'll come back to it if it's interesting. I mean, if it's interesting to you. So that was all the fault tolerance part. The horizontal scalability part is very similar to what a lot of other people are doing. It's basically sharding. We shard based on the directory component of an object's name. So if I'm looking for dap public bin devzone setup, we'll shard on dap public bin. And the reason for that is that allows us to make sure that all of the objects that are stored within a given directory, all their metadata lives on a single Postgres database, which means that we can do lists pretty efficiently. If we had to be bouncing across a whole bunch of different shards in order to do an MLS operation, that would be really problematic. We use a consistent hashing implementation, and it's hidden behind a service called Electric Moray, which just sits in front of a bunch of Moray shards and uses the hashing key to figure out which shard to direct your request to. So it's pretty straightforward, I think, what a lot of people are doing. All this stuff is open source. There are a couple of different repos that are interesting here. One is Manatee itself, which is github.com Joyent Manatee. I apologize in advance to the people in the room who have worked on this from the community. We have not been great about keeping up with all the issues and pull requests, but there is definitely interest in improving that. And the source is out there. There's some documentation out there. If you have any issues with it, let us know. The Manatee state machine is a separate repo, and this implements the crux of the algorithm that I was talking about earlier. So this is the bit that keeps track of, through interfaces, it keeps track of Zookeeper state and Postgres state for an individual peer and decides what the next thing it should do is. So it's completely self-contained. It has a little simulator in it where you can basically bring up a fake cluster and say, okay, I've got n of these nodes, and I'm going to pretend that this one's primary. Now I'm going to write this new cluster state and see what happens and things like that. And it's got its own test suite as well. It also includes a more formal write-up of the stuff that I just hand-waved over around how these transitions actually work. So if you're interested in that, check that out or ask me. Moray is also up there, and Manta is here as well. So Manatee today, where are we with this? We're actually still running version 9.2 of Postgres. I'm curious, how many people out there are still running 9.2 of Postgres in production? Okay, so there's a couple. How many people are running anything older than that? Okay, I think about the same number or more. What about 9.3, 9.4? Okay, so most people have moved on to 9.4. This is a huge problem for us because of the duty cycle thing I talked about earlier. We haven't spent enough time looking at this, and it may be that there's an easier solution than I know, but we can't take Manta down for many hours to go rewrite the database. So that's basically the reason why we have, and we can't do replication across versions. So that's why we haven't upgraded. We're still on 9.2. Moray Manatee itself is integrated into our Manta deployment in production in US East region. So our production deployment is in 3 availability zones in a single region, and each Postgres peer for each shard is in one of those availability zones, which means that we can survive availability zone failure, compute node failure, and all that good stuff. It's also, this whole stack, Moray Manatee, is used in Smart Data Center, which is the product that Joyent, we sell as an on-prem product. It's an open source project. It's a cloud orchestration framework. It runs the Joyent public cloud. So anytime you go provision containers or create a new user account or any of that stuff in our cloud, you're using SDC, and you're interacting with the Moray Manatee stack because that's where all the data in SDC is stored about users, networks, containers, VMs, compute nodes, all that good stuff. So we're actually using this basically everywhere, all the time. How am I doing on time? Doing okay. Okay, so one use case I want to talk about is our use of Manatee Moray for the compute jobs that I showed earlier. Remember earlier I did a very simple job where I just did a find over a couple of objects and then did a word count on them. But the idea with Manta jobs is that we want to be able to support an unlimited number of inputs, outputs, and tasks as part of these jobs. And because we already had this Manatee Moray thing, we were like, well, let's try and use that for the jobs tier. We initially tried to use it as kind of a queue where we would basically like keep track of which transaction ID we were caught up to, and then we discovered that transaction IDs were not sequential, which is, that's an example of one of the really silly things that we just did up front. What we ended up doing is changing this to a system where all of the queries by all of the components are done based on state that's stored in the record. Because it's like, what is Postgres really good at? Well, it's good at doing queries with where clauses based on state that are represented by values in these rows in certain columns. So it's like, let's make the thing that we're interested in based on that. Obviously, I'm not going to go through this whole state machine. This is a very simplified version of what happens when you run either a map task or a reduced task through a Manta job. So the basic idea is if you submit an input to a Manta job, we write a row into a Postgres table that says there's this input for this job. Some other component is querying for those things and saying, okay, I need to take all those as they come in, locate the corresponding object, and issue a task for a particular agent that is going to execute it on that box. The agent is going to query for those records, and it's going to say, oh, I'm responsible for running this. It will go run that task and write the result out. And so these components are basically handing off ownership of these objects as they execute things. This is all through Moray, so these objects they're basically just JSON objects. The first problem that we ran into operationally with Postgres, basically at all, was around job performance. We would have situations where jobs became really slow. A 7-second job would take like 10 minutes. Like you would literally run a job that was a reduced task that operated on no input and ran the date command, which like 7 seconds is actually pretty generous for that, right? That's like a whole bunch of round trips to the front end to set this whole thing up. And that would take like 10 minutes. And the reason was that all these components are doing all these queries for information about their jobs, about the records that they're responsible for operating on, and those queries would take minutes at a time. And the question is why? Well, the typical reason was that we didn't have auto vacuum and auto analyze configured properly. And this was exacerbated by some other stuff that we did where we would, for example, if you created a job with 8 million inputs, when we went and purged that job, we would go delete 8 million things in one transaction, which meant that there was a very long transaction during which time you have all these tuples that are being created by all these other jobs that now have to be held onto. They can't just be cleaned up because there's other transaction that can see them. It ends up getting pretty bad. What was really cool about this from my perspective was the Postgres documentation for explain is great. I was able to go look at the queries that were happening and figure out exactly why this was taking so long. And it was kind of interesting. What was happening was if you just think about the inputs for jobs, all of the inputs for all of the jobs are stored in one table. So there are, say, 6 different job supervisors that are running at any given time, and they're querying for inputs for jobs that they are responsible for operating. And they're doing that based on their own ID. Well, if I go create a job with 8 million inputs, then I greatly skew the distribution of that particular value in that table. So I have a table that might have like 9 million entries in it, of which 8 million are for one specific supervisor. The query planner figures this out because it's doing periodic analyze operations and says, well, if you're looking for that thing, if you're looking for records for that, I'm actually just going to do a table scan because it's going to be more efficient. But the next day, when we've purged that job from the database, because we purged them after 24 hours, that distribution is totally different. And the query planner makes a decision like, I'm going to do a table scan. It's like, no, don't do a table scan. That is definitely the wrong thing to do on this particular table. And the problem was that we weren't running analyze enough. So this was something we did eventually correct by effectively just really aggressively auto-vacuuming and auto-analyzing. Even that, I'm not sure how well we've totally nailed it. There's the solution of putting cron in a cron job that just does like an actual vacuum analyze, which we probably should look into. The problem is, again, the 24/7 duty cycle. We can't take like a 10-second blip every day at midnight because we need to do this thing. We really would rather pay that cost amortized. We'd actually rather have every transaction take a little bit longer than have that variance just like totally randomly. The second incident that I want to talk about is that we had various queries hang. This one turned out to be totally on us, as most of them ended up. Well, I shouldn't say totally, but what would happen is we'd walk up to a box and we'd discover that all the queries for the Manta database were just totally hung. We could do other queries like select now or something like that was fine, but if we do queries on the Manta table, all of a sudden those things just hang. And what we quickly were able to go see that the oldest query in the database, or the oldest running, what do I want to say? I think it's the oldest open transaction that was currently there had been open for several minutes at this point, which is basically when the incident started, and was run by some client. And we have the IP address of the client, and we go over to the client, and the client has no idea about this thing. But the client did log something about that time saying that it had some error processing the result from the database. So what we believe happened at this point was the client does like a select for update. And then as it gets these rows, which will find a bunch of rows and then take a lock on those rows. As it's getting these back, it encounters an error. And this was a node program, it would throw an exception. Now normally what would happen is that node program would exit, and all those sockets would be closed, the database connections would be closed, the things that it was doing would be aborted, and things would basically be fine. But there's this sort of separate problem, which is definitely not related to Postgres, about software development in general. People really don't like it when software crashes. So they do things like, let's add an uncaught exception listener, which causes the thing to not crash. So it actually just like logs this error, but then barrels on. But it's tautologically, it's something that you didn't expect, because it's an exception that was thrown that you didn't catch, and it wasn't something that you had built any error handling code for. So for us, we found, in this particular case, the uncaught exception handler logged the error and then allowed the program to just keep running with the file descriptor open for an open transaction with locks held in the database, and that caused basically all the other queries that we were trying to do on that thing to hang until someone had come in and reset it. That was kind of an interesting lesson for us. The next one I want to talk about was probably the most serious outage that we had with Postgres. So this was, again, another situation where we walk in and we find that queries are hung to all the Manta table, all requests on one shard are basically just totally hung. And the other thing we noticed, we didn't know if it was related, was this auto vacuum was running to prevent wraparound. How many people here know about the transaction wraparound issue? Actually, a lot of people know about this issue. That's great. I knew enough about this issue at this point to think that it was a serious issue and that we better not try and cancel this thing. We actually need to let this thing finish, which was actually a mistake in retrospect. But, well, to be fair, we did try to cancel it first. We did cancel it, and it kicked off another one, which also makes sense given what we understand now. But just going through from the perspective of where we were at this point, we said, okay, well, this thing obviously has to complete. Postgres obviously seems to think this is a pretty important thing to do. So we're going to try and make it go as fast as we can. And we start doing some unholy things to do that. We found that it was reading files sequentially in a directory, which most file systems optimize and do prefetching for a single file. But at least ZFS doesn't do prefetching for multiple sequentially named files in a directory. So we start prefetching all that stuff. We also found that the auto vacuum process itself was sleeping every whatever it was the period for like 10 milliseconds, which again, the point of this is to create liveness in the system, to allow other things to make progress. Problem was, everything else in the database was actually blocked on this. So sleeping was definitely the wrong thing to do in this particular case. So I don't think that was dynamically tunable, but it's our computer, we have a debugger, and we were able to whack that and make it so that it stopped sleeping so much. Definitely a little bit scary, but it needed to be done at the time. So about 5 hours later, this thing does complete. The auto vacuum completes, the service comes back online, everything is happy for like 5 minutes. And 5 minutes later, it starts up again. Another auto vacuum starts up that says to prevent wraparound. And this one we haven't root caused. We don't know why this has happened. This happened to us again. This happened to us in a couple of other cases. We would do an explicit vacuum analyze, and it would print out a bunch of output and say, okay, I did it, but it wouldn't update the vacuum time on the table. And it sort of seemed like it didn't actually work. And in this particular case, we had an auto vacuum, which was a freeze auto vacuum, which did not update the table's freeze age. So that's weird. We haven't figured out what that one is. At this point, we don't even know that much, though. But we did discover enough okay, we realized we needed a new approach here. We couldn't actually just let this thing finish because we weren't sure it was converging. So we found the auto vacuum freeze max age. How many people have tuned this up before? Fewer people than know about the transaction wraparound problem, which is interesting to me. So the transaction wraparound problem happens at 2 billion transactions. And Josh actually has a great set of blog posts describing this problem, which were extremely valuable for us. So thank you for doing that. We got out of this outage by just tuning this up. Obviously, that doesn't fix the problem, but it got us out of the outage. And it allowed us to gather enough data at the time to root cause the problem and then figure out how to actually fix it. And so at that time, we were looking at we didn't know why anything was blocked, but we knew enough to know that it might be related to locks. So we gathered basically everything in the PG locks view to see what we could figure out after the fact. Then we tuned that thing up, and we were happy. Question is, why were we blocked? We wrote a little tool to summarize the locking relationships between all the things. And it's a little bit unwieldy if you look at it yourself, because you've got records for everything that wants a lock as well as everything that is holding a lock. And so we have 1,000 connections at any given time, so there's a lot of different possible relationships there. The root cause turned out to be the fact that we had this drop trigger query, which is kind of a weird query. This is kind of a like one-off little part of Manta, which is that if you have objects with very large numbers of directories and you do an MLS on that, the API actually tells you how many objects are in that directory. In order to do that, we don't want to do a select count every time because you might have 1 million objects in that directory. So we keep a separate table with the counts of objects in each directory. And in order to maintain that, we have a trigger on the main table that increments or decrements the counter using what is basically an upsert, if you went to the various talks earlier today that mentioned that. In order to make this work, we have to install the trigger. In order for the trigger to be installed, what happens is basically every time we connect to the database, we would drop the trigger and create it again, which seems a little bit weird, especially if you know what's going on under the hood. You're like, don't do that. Definitely don't do that. That's because it turns out drop trigger takes an exclusive lock on the whole table, so it stops any activity that's going on. We had not noticed this before because it's actually pretty quick, so it's not that big a deal. So we were basically just doing this as an idempotent way of making sure that the thing is always there. Basically, whenever this code runs, it's just going to drop it and create it again. Here's the problem. The problem relates to the way the locking works inside of Postgres. So Postgres has something like 6 or 7 different types of table locks, and they differ in terms of the kinds of other operations that they exclude. And there are 3 interesting classes from our perspective. The first is this access share lock, which is used by our data path. The second is the share update exclusive lock used by the auto vacuum. The important thing is that neither of these conflicts with the other. They don't conflict. You can have as many data path operations going on as you want, and as many, if you had many auto vacuum operations going on, that would be fine. The problem is that the drop trigger wants an exclusive lock. And even then, it's like, well, why wouldn't the drop trigger just block forever? What happened basically is that when the drop trigger shows up, it becomes blocked on the auto vacuum as well as all of the data path queries that we were trying to run. But the data path queries are totally fine, so they actually end up all completing. The auto vacuum is going to run for whatever it is, 5 or 6 hours. But at that point, all the new data path queries end up blocked on the drop trigger. And this might be a little bit surprising if you are, if this just isn't something you spend a lot of time with, but it makes sense for reader-writer locks. It's basically a reader-writer lock, and if you don't have this behavior, then it's very easy for writers to get starved, because as long as you have at least one reader, then the writer can never get in. So all the subsequent data path operations end up blocked behind the drop trigger. The drop trigger is blocked behind the auto vacuum. So it's not a deadlock, actually. It's just a three-way lock relationship that destroyed the liveness of the system. What's a couple of interesting points about this. Obviously, the problem is not Postgres, really. The problem was our application doing a drop trigger. It really shouldn't have been doing that. That said, there's no way we could have hit this without the wraparound auto vacuum. We couldn't have hit the outage. And this was something that I'd welcome clarification on. I did not find any documentation explaining this, but I did find some mailing list posts explaining that a regular auto vacuum will back off on locking. It's either drops locks or it won't take all these locks. I think it won't hold them for very long. But a wraparound auto vacuum is special. It actually won't drop those locks because it perceives that this is a really important problem. We would need to shut down the database if this problem got bad enough, so we want to really deal with it. But as a consequence of that, it took a wraparound auto vacuum for us to hit this problem, which means it would have been pretty hard for us to have hit this in testing or in staging because it really just happens for being up for so long. That was the problem. The other thing that was challenging about it for us was that when I went to go fix this, what I was doing was changing the code to not do the drop trigger or not do it if it didn't need to. So what it actually does now is it checks if it's there, and if it's not there, then it creates it. And it's a version thing, so it's more complicated than that. But essentially, what I would like to do now that I've fixed this is verify that my application is no longer trying to take any exclusive locks. And I don't know how to do that actually with Postgres. You have the PG locks view, which shows you what locks are being held right now, or which locks are wanted right now. But that's a sampling view. So if something is being taken and it's just granted instantly, you could easily miss it, right? Now, there are dtrace probes that will show you when you start waiting on a lock, and I ended up using those. I basically created lock contention and then used that probe to measure that I was not actually trying to take any exclusive locks. But it'd be really nice if there were a way to say, walk up to your database and say, show me what locks are being taken right now at all, like as a count over time, and not missing anything as a result of sampling, but actually counting everything. That would have made this problem a lot easier, and it would also help people who, if you just want to walk up to your database and make sure that you're not subject to this problem, I'm not sure how you would do it today without that. How am I doing on time? Like 10? What's that? 13? Okay. This one, I actually thought this was more humorous than anything. Mostly, it didn't hose us all that badly. We decided, for whatever reason, in our application to create one table per some object that we actually had a lot of, and so we ended up creating 70,000 tables. But we backfilled this. We did this as part of a software update, and we backfilled it when the software update was deployed. So we created 70,000 tables around the same time, which means that their transaction wraparound happened basically almost at the same time. We basically had this sliding window of transaction wraparound for all of these tables, one after another. Fortunately, all these tables were tiny, and we also weren't doing any drop create triggers on them. So the biggest problem that we ran into was actually that the stats collector was constantly rewriting its file, which was 130 megabytes. This is, I'm not sure if this failure mode is exactly documented, but the problem is somewhat described, and you can configure Postgres to write that to a RAM disk or some other file so that you don't have that problem. That particular problem ended up being, it was one of these ones where you have a database that's behaving a little bit slowly. Like queries are taking like 2 seconds instead of 100 milliseconds, which is bad, but like they weren't super fast to begin with. You walk up to it and you're like, boy, it's doing a ton of I/O. And the reason it's doing I/O is that it's rewriting the stats collector file time and time again. We were able to use dtrace to figure that out, though. We built a bunch of tools as part of just this general work. I talked a little bit about PG lock analyze. It's pretty specific. This would be if this would be interesting for a case where you either have a deadlock or some weird locking interaction. You have the output of the PG views table, and you just want to summarize that. So what this does is it looks at all the dependencies in the locks and says, what this boils down to is there are 990 queries that look like this one that are blocked on this one, on this particular thing. And that one is holding this lock, which this other thing is blocked on. So that was kind of useful. PG StatsMon was a little thing I threw together basically actually to test out statsd. We just wanted to play around with statsd and Graphite. This basically uses the Postgres client interface to fetch a bunch of stats and shovel them into a statsd instance so you can just graph that stuff. But it turned out to be pretty useful for monitoring the table freeze age right after we'd had this outage, we wanted to see how close we were to it after that. It was easy to just add that to it. So that could be useful as well. And then there's this sort of small suite of tools called PGSQL stat that I thought I would demo, because that's actually been kind of useful. So I am sitting in my test machine again. I'm not sure if I'm in the primary peer. I am in the primary peer, so I should have these tools here. So one thing I added was this PG lock weights tool, which is not going to be interesting here because, like I said, this only shows locks under contention. So the locks are not contended right now because we're only using the reader locks, so that's actually totally fine. When I was doing something that would take an exclusive lock, this would show data in the X column for exclusive lock. So what this is showing you, I should back up a little bit. All of these tools use dtrace. So there are a bunch of dtrace probes sitting in Postgres, which means that you can walk up to any, I mean, if your system supports dtrace, you can walk up to any Postgres installation without having configured this or turned it on or anything like that, and see information about what's happening across all the Postgres processes, including multiple databases as well. So I should probably show this on something that's not just all zeros, though. So this is showing the number of lock acquisitions under contention in each second across the entire system. Probably a more useful thing, a useful top-level thing is this PGSQL stat. And I'm going to give it 1 to say print out every second. What this is showing is the number of queries that are started and completed every second, as well as the number of transactions started and completed and aborted, wall entries inserted, number of sorts, buffer reads, buffer writes, and dirty buffers written. This is basically just because these are what the dtrace probes were that were there, which I knew what probably half of them were, and I kind of figured that whoever added the probes thought that was a useful thing to keep track of. This is a useful way of walking up to a database and seeing how much work it's doing. PGSQL lat is another one. So I'm going to do this for longer. So what this is doing is it's tracing all query latency. I'm giving it 10 seconds here. So it's tracing start to end for all queries and showing you the distribution of time spent in microseconds. And it also gives you this, boy, I don't know why the terminal stuff is kind of looking weird, but so what we have here is a visual plot of the distribution over time. So that's one plot per second. So y-axis is query latency, and the height of those little blocks is the number of queries in that bucket. And here we have the same thing for the overall period. So we can see that like most queries took between 50 and 60 microseconds, and they're sort of a little bit longer tail. A couple of other things that are interesting. There's PGSQL slower, which I think is a pattern that people have probably seen before, which is showing you queries that are slower than 5 milliseconds in this particular case. But of course, I just showed that all of them were much faster than that, so we're not going to get any output. If I do 0, though, then we'll see all the queries that are taking longer than that and how long they spent in each of these various phases. Completed queries, yeah. Someone asked if those were completed queries. Yeah, those are complete. What's that? One that was in flight wouldn't be noticed. That's right. So that's actually a limitation of the way all these tools work, is that since they're tracing from start to end, they won't catch anything that has been running for longer than they have. So if you started a query 3 hours ago, it's never going to see it. So it's useful if you are either running this constantly, so you're pretty much going to catch everything, or if you're interested in a lot of, what I found was that if I was interested in a really long query, I could use PGStat activity to see that stuff. What I had a much harder time seeing was the stuff that was really quick, but happening a lot. Or even not that quick, like 3 seconds, but it's long enough that I don't actually have time to physically find it and then like go figure out which Postgres process is doing it. So that's kind of why I built this stuff. But of course, the things that are actually taking a while are begin, transaction, and commit, or that's the thing we're seeing a lot. What tends to be more useful is this PGSQL TX slower, which is things that are slower. I guess I'm going to have to, oh, that worked. So this is showing for transactions that are slower than that, more information about all the queries that were run as part of that transaction and all the things that were done in each stage of processing those queries. So we had a begin, transaction, isolation level, repeatable read. Then we have our select, limit whatever. We do another select. And those are actually the only 2 things we did here. But we did a couple of parses, rewrites, and executes, and plans. And no sorts. think those are the interesting tools there. Okay, so I talked about a bunch of the kind of sillier stuff that we did. I'm not going to go through it all again. I talked about the not yet root caused issues that we have run into. Another one we've run into a couple of times is Postgres crashing on startup during wall replay. It's pretty rare, but it's obviously pretty scary when it happens. We did get one of these fixed already, and we need to actually get on the other ones. To be clear, the durability and performance of Postgres have been great, and we've never looked back. And the observability has been really clutch. For us, the ability to gather data during an outage and be able to fully root cause it and feel like, yeah, we really understood why this happened is so valuable. And it sounds obvious. Maybe this is true for everyone, but it's certainly true for us. So having the dtrace probes, having all those internal views is really useful for us. I think I'm just going to skip over that because I'm basically out of time and wanted a few minutes for questions. So I have like 3 or 4 minutes if people have questions.
So you said
Yes.
you on 9.2, does your code depend on 9.2 or you just didn't have community upgrade?
It's a good question. Do we depend on 9.2 or did we just not upgrade? We just haven't upgraded. We don't know of any dependencies on 9.2. And in fact, I believe there's someone in the community that's been running on 9.3 and 9.4. So there shouldn't be any dependency there. That's good, yeah. Yeah. Definitely, yeah. We've generally not had problems when we did upgrade. We've upgraded within the 9.2 stream a few times, and obviously that's been fine.
Don't you think the drop trigger full table might be out in 9.5?
Yes, I found that out in the talk this morning. I was very interested about that the drop trigger, the locking changes in 9.5 may have changed things so that drop trigger no longer takes an exclusive lock, which would have saved us a lot of time, which is great. It's a great change. Glad to see it come in. I hope that the tone came off appropriately here because Postgres has been great for us. We've run into some issues, most of which were caused by us, some of which there are some things that we wished Postgres did better, and we're trying to provide that feedback where it makes sense to do that. But we've been very happy with it. Yes?
Scalability code, does it allow to maintain multiple clusters easily?
So the question was, I believe, about the Manatee project, whether it allows you to maintain multiple clusters easily. There's no, we have code that manages multiple clusters. It's done at the application that deploys those clusters level. Manatee itself doesn't really. The one thing it does is if you do Manatee ADM show, it'll show you which shard it is, and you can give it an argument that refers to a different shard. So you can say, I want to know about the other one. But it doesn't, other than that, that's all the tooling there really is, I guess. So I guess it is basically fine, but there's no rich support for the horizontal scalability aspect. This was really just about the fault tolerance. And at the Manta level, we have Manta ADM show, which shows you all the different clusters. Yes?
Can you give us a feeling for how much data you have in your production system?
Yeah, so the question is, give a feeling for how much data we have in our production deployments. This is totally, I'm not totally sure about it. I believe it's on the order of, I think it's several hundred gigs in each shard, and it's about 200 million rows in our main table. The rows are pretty small, and we basically just have one table for Manta. The jobs table tend to be much smaller because they're just whatever activities happened in the last day.
Why not merge this tool into core?
What's the question?
All these tools, good tools that you have, why not merge it into the core Postgres code?
Oh, the core. So the question is, we have these tools. Why not merge them into the core Postgres code? Not any particular reason. I guess it wasn't totally obvious to me that some of that stuff would make sense there. But if that does, then I'd be happy to submit that upstream. Cool. Okay, I think I'm about out of time anyway. Thank you.